Alright, so I am on slide 27. We're going to finish up empirical formulas and get into molecular formulas. Alright. Okay, so we went over empirical formulas. Remember the lowest reduced formula. So in this case, if I have the molecular formula C2H10O6, it could all be divided by 2. And so in this case, it would be CH5O3, right? That might be my empirical formula. Now, what we want to do today is we want to see, once we've determined the empirical formula, we want to determine the molecular formula. But what I want you to see also is that there's an infinite amount of possibilities when it comes to molecular formula. For example, CH2O, right? Its molecular formula could be CH2O, couldn't it? But it could also be a multiple of some sort. It could be C2H4O2 or C3H6O3, right? Well, all I'm saying is that once you have the empirical formula, you can figure out the possibilities of the molecular formula. They're going to be a multiple of the empirical formula, but we don't know exactly which molecular formula it's going to be. We just know the possibilities. Why don't you try these on your own? You can pause the video. So possibility is C2O, right? Could be C4O2, C3. I guess it can't be C3. C6O3, so on. C12H22O11. That could be C12H22O11. One possibility could be it itself. It could also be C24, H44O22, and so on, right? So anything along these lines is fine, as long as it's some type of multiple. So I just want you to see that, be able to go between molecular formula and empirical formula by dividing by the greatest common factor here, but also understanding that if you have an empirical formula, you can figure out possible molecular formulas. It's going to be a multiple of the empirical formula. However, you don't know exactly which molecular formula it's going to be. You can only determine possibilities. However, in our first problem, though, we actually can determine a molecular formula from the empirical formula. So it says the empirical formula for acetylene is CH. If it has a molar mass of 26.0 grams per mole, what is its molecular formula? What that means is that the molar mass of acetylene is 26.0 grams. Let's first figure out, so we got to figure out what multiple is acetylene from CH. Is it C2H2? Is it C3H3? Is it C4H4, right? Like, we have to figure that out. So this would be a multiple of 2, this would be a multiple of 3, and this would be a multiple of 4. Well, how would we figure out the multiple? To figure out the multiple, you first have to figure out what is the molar mass of this empirical formula. Well, C and H is 12.01 plus 1.01, which is 13.02 grams, right? If the molar mass of acetylene is 26.0 grams, right, I can figure out the multiple by taking the molar mass, 26.0 grams, here's your molar mass, and divide it by the empirical mass, 13.02 grams, right? And you'll see that the multiple is 2. And so acetylene is just doubling CH, right, which is going to be C2H2. Now, if you think about it, right, C2H2 is, so CH, its molar mass is 13. This one's going to be 26. This one is 39, right? And this is whatever, 4 times 54, right? So these are all multiples. These masses are all multiples of 13. So we figured it out this way. Okay. So what's the next step? Well, instead of giving the empirical formula, we might ask you to solve for the empirical formula and then figure out the molecular formula. So let's go ahead and do this example. First, we have to figure out the empirical formula. So we have the percent composition. So this is something we've done before. Remember, if you have a percentage, you can assume that the sample is 100 grams. So you have 40.68 grams of C. So why don't you try this on your own? You can press pause, try it on your own, and I'll go over it with you. See if you remember how to do it. So first you want to convert to moles, right? So you have 12.01 grams of carbon over 1 mole. Remember, this is like yesterday's hydrate, right? And so that's why we teach this together, because they're all super similar to each other. And then oxygen is 16.00 grams. So remember that this is all within a chemical compound, and so we don't worry about diatomics since they're not by themselves. So 40.68 divided by 12.01 equals, so this equals 3.387 moles of carbon. 5.08 divided by 1.01. This equals 5.030 moles of hydrogen, and 54.24 divided by 16 equals 3.39 moles of carbon, or sorry, oxygen. Remember, we divide by the smallest number, so 3.387, 3.387, and 3.387. This one might be a little trickier. So 5.030, this is going to be 1, this will be 1 as well, divided by 3.387. So this equals about 1.5. So here, we haven't gone over this, but remember, we're looking for whole numbers. Like, I can't write C1H 1.5 and O1, right? I can't write that. So what I'm going to do is I'm going to multiply by a number that'll make it whole numbers. So if we multiply everything by 2, that 1.5 will now turn into a 3, right? And so my empirical formula is C2H3O2. Now, we now have to go back. The molar mass is this amount, right? This is the empirical formula. So remember the molecular formula. So this is empirical. It could be like, it could be C4H6O4, or it could be C, what else could it be? What, like C8H16O6. So it could be several things. We just got to figure that out. So first, we know the molar mass of the molecule is 118.1 gram. So the empirical formula is going to be what? So let's figure out. So this is like the problem we did before. So what I got is the empirical formula is 59.04 grams per mole, right? And so we know that C2H3O2. Now if we take 118, which is our molar mass, divide that by 59.05, we should get 2, which means the molecule itself is double the empirical formula. So that would be, if I double the empirical formula, it's C4H6O6, right? So this is succinic acid. That's the molecular formula. So just to recap, we solved the empirical formula, then we figured the mass of the empirical formula, which is right here. We divided the molar mass by the empirical mass to get the multiple, and in this case it was 2. All right. Why don't you try this one as well, and then go ahead and press pause, try it, and then we'll check your answers. So 34, oops. 4.95 grams of carbon. We know that there's 12.01 grams of carbon in 1 mole. 6.844 grams of hydrogen. 1.01 grams of hydrogen for 1 mole of hydrogen. 46.56 grams of oxygen. 16 grams of oxygen, 1 mole. Oops, sorry, that should be oxygen. And then 13.59 grams of nitrogen. So remember, what I did is I I made everything out of 100 grams, so those percentages could just simply go to grams. All right, so it's 34.95 divided by 12.01. I get 2.910 moles of carbon. 6.844 divided by 1.01 equals 6.776 moles of hydrogen. 46.56 divided by 16 gives you 2.91 moles of oxygen. 13.59 divided by 14.01 give you 0.970 moles of nitrogen. Remember, divide by the smallest amount, that would be 0.9700. So 2.910 divided by 0.970 give you 3. This is 1, right? 6.776 divided by 0.97. Oops. 6.776 divided by 0.970. This gives you about 7. 2.91. Well, we know this is about 3. All right, so we have to figure out the empirical formula, right? The empirical formula is C3H7O3N. All right, so remember, so we figure out the empirical formula. It says the molar mass is 100 grams per mole. So we first have to figure out the mass of C3H7O3N, the empirical formula. So let's do that. 12.01 times 3. Oops. 12.01 times 3 plus 7.07 plus oxygen. 16 times 3 plus 14.01. About 105.11. So this equals about 105.11 grams per mole. So actually, the molar mass and the empirical mass are actually super close. So the multiple probably is 1, meaning this, the empirical formula and the molecular formula are the same, because the molar mass and the empirical mass are the same as well. So this is probably what the serine is. This is an amino acid. Okay? All right, so let's take a look at the homework. So you have a quick check tomorrow on this. I have practice of writing empirical formulas and then 4 problems calculating molecular and empirical formulas. You'll notice on the key that I have answers, and then I'll also show my work so you can kind of see what I did. All right?